I'm Rob Stevenson, and I teach at UMass Boston the biology department, so it's a little unusual that I would be speaking about drought, but I have a degree in civil engineering too. And for many years, I lived in Newburyport and occasionally would get over to the Parker and poke around and documenting a little bit of the drought and realize it was there. But now I've moved from Newburyport right to the on West Street in Georgetown, right next to the river, the upper main stem of the river, and go by Lufkin Brook every day. And so I see the river, I see what's happening every day, and I see the beauty of it and the challenges it faces from water flow. And so I work with Parker River Clean Watershed Association, where I am on board member for 25 years, to write a little grant from the Water Resource Research Center at Amherst to look at drought and water quality, that combination. So I got more and more interested. And George Kaminsky, the last maybe 15 years or more, has always been talking about this and saying we got to be more. And so this is our chance to do a little bit more. So George's help and other people, and in particular, we started to do a little bit more serious work. And so what I'm going to show you today are some analyses of data. And we're very blessed because the USGS has been taking data for a long time. So you can make inferences about what's going on. The second thing I wanted to say is that I didn't appreciate for a long time that Georgetown is taking its water out of an aquifer which lies just below the river. So think of it as a river in the soil too, in the gravel beds, and we only see the top of it, what we call the river, but the river's flowing underneath. Okay, and that brings me to the last point, and that is, as I leave my house every day to go to work in Boston, I drive by the Georgetown water treatment supply plant where they pump the water, and there's a nice sign that says public water supply. At the top of the hill, I turn to go onto 133, and there's the golf course. And there's a big sign out front that says private wells. And it's something that we have to deal with as a community, because it is a private well. There's no question about that. They build the well, but they put the straw in a public resource. It's a public resource. It's not, they're trying to imply that it's our water. And I don't believe that's true. I think that's a mistake. I think that's not the fact. So we as a group and people in general have to recognize it's the same way with clean air, right? It's a public resource. It's not for private use only. So that's a big issue that we need to think about. Okay, just a few pictures here about the drought. This is the building you see is one of the pumping stations on the Parker, and the marsh has gone dry. And there's a few more pictures. That's Bull Brook on the left, and on the right is Lufkin Brook. And that heron is having a great time because all the fish, the rest of the river is dry. There's the fish, mostly bull pout, the catfish-like fish, are all concentrated. There's hundreds of fish in there, and they're eating the last ones. There's no place to hide for the fish in the drought. That's another picture of Bull Brook, just to show you the beaver deceiver is no need for that anymore. The beavers have to go somewhere else. Looking upstream. You got lots more pictures. That's the marsh by my house, right near the Georgetown wells. Okay, so to get data, we have the USGS, and there's two sites now. Do people know there are two sites to look at the water supply? There's the new site and the old site. So you can go, and here's the new site. That's what it looks like. It gives you this wonderful bar that shows you what's happening right at this time. And here's the latest value in the river, daily stream flow. Look at the lowest value. The lowest value is much higher than what's the actual value. So this is a record low by a long shot. Here's the 25th percentile, there's the median, there's the percentile, and the highest value. The other thing to notice is look at the range of flows. 0.27 cubic feet per second versus 116 cubic feet per second. That's 3 or 4 orders of magnitude, right? That's an incredible change, and that's characteristic of rivers. So when things are high, well, water's everywhere. We can take a little bit out, it doesn't matter. But when things are low, I'm going to try to convince you it really matters. Here's an actual record for the year, and it gives specific values where that tab is. But what you can see is that it's high, it's 40 to 60 cubic feet per second. And then in these months here, June through August, it comes down and it gets really low. It's really low. It looks like zero. On an axis like this, we call that a log axis. Is that familiar to people? On that log axis, you can never get to zero. So this is a combination of 2 graphs, but they're calling that zero. And the gauge will read zero because it can't read low flows. It's effectively zero. The other thing that you can see very dramatically here, you can see an event like this. And that, of course, is a rainfall event. That's what that is. What's happened is we've got a rainfall, the water flows off the top, it goes way up, and then it comes down gradually like that. And that gives us information about how the watershed works. And I haven't analyzed any of that, but I think there's lots of information, valuable information to get from that. Here's what the old site looks like. And the good thing here is you can get records from starting in the 1940s. So if you wanted to detect climate change, this long record might give you a chance to do that. Okay. Now, when you get data, the first thing you're supposed to do is look at it, just to see if it's clean, to see if you can make any sense of it. We're in the era of data science now. You may have heard that term, right? Data is coming quickly from instruments, and there's a ton of it. And how do you make sense of it? So that's what I did. I got all the data. I just started to make sense of it, and that's what I got. Okay, and so you can see that the mean is maybe 20 cubic feet per second in January, but there's a lot of variability. It can go almost down to 1, and it can be more than 100. The highest values there are up at 800 cubic feet per second. That's a huge event, right? That's a huge flood. That's a real problem too. But what we're really interested in is this time here, low flow. We're interested in droughts. And you can see those pulses where it seems to be spiking, coming down. That's another rainfall event. Those are just big rainfall events that aren't in the map. Those events are occurring all through here. You can't see them. The other thing that's very important to notice is look at this, the striping here. See that striping? That's the resolution of the gauge. The gauge can't measure in between there. So you're at the bottom end of what the gauge can measure. You can sort of see a few bumps there too. Right, so it can't. On a log axis, you're never going to get to zero, but you can see that you're at the resolution of the gauge there. Does that make sense? Yeah. Does anybody have any questions about this figure? I should say too, if anything occurs to you, or if you're puzzled by something, don't hesitate to raise your hand, and we can have a talk about it. This is a very informal talk from my point of view. I didn't polish this up the way I should have as a professor, right? But it's not polished at all. And that's because in some ways I'd rather have a conversation. I've come to believe that as much as I would like to be able to open up your head and pour information in, it just doesn't work that way. Lectures are great, but yeah.
So is the current year one of those bright lines down at the bottom?
What about that?
Is the current year data one of those?
It's actually, I'll show you a bit, but it's mostly 2016 and 2022. Those are by far the lowest flow years. And I can't, I don't have a great graphic for that yet. If people have an idea, George gives me a couple ideas, and I try to pull things that I'm just not that quick at the R skills yet to make it beautiful. But I can talk to you more about that. I think that's the most important thing to show people, actually. So this is just to show you that there's cycles. And it shows the high flow, and there's big events here. There's 6 big events from about 1980 to 2010, where I got super big flows, where they didn't seem to be that big, earlier on. But we're interested in the low flow stuff. So here's my big figure on that. This is a complicated figure, so I'm going to walk you through it slowly. First, here we have the x-axis, okay? And here we have the number of times in a year that the flow was less than 1 cubic foot per second for the daily average. Okay, so this would be 1946, and the flow was below 1 cubic foot per second about 30 times. Does that make sense? Does anybody have any questions? Can you understand that, what that bar means? There's one confusing part to that, and that is, it actually tells you here what month that occurred. So this one occurred in November and October. Yes.
So based on the coloration,
Yeah.
it looks as though it never happens between the months of January and May.
That's right. It doesn't. The river never goes low during those months. Those are the cool months, and that's, I'll tell you a little bit more about why that is, but go ahead.
When did the Georgetown wells go in?
When does the what?
When did the wells go in?
When did the wells go in? I don't know that. And I don't know what the pumping rates were long ago. They're not copying that data up. I have some data for them, but we haven't been able to extract that data. Yep.
Yeah, so it would be interesting to see your precipitation, because obviously it's gonna fall probably the.
You're absolutely right. Why is precipitation so interesting? Because that's the input.
And not just that, the population. So
Yeah.
the census data and see.
Yeah.
Where that's going, and that should affect the.
So if I had 10, we're gone. You're absolutely right, and I'll show you how far I've got in that. But all these questions are exactly. You guys are way ahead of the average person, I think. You're all environmentalists who've been thinking about this for a long time. Okay, so we see some groups here, right? And here in the 60s, there's a pulse of times when there was low flow, right? And then there was a time around the 80s again. But look, it looks more frequent now. I think this looks, I haven't done any statistical tests, but it just looks like it's happening more often, and it's happening higher rates. Okay? Does that make sense? Any questions about that? Now, if we go to 0.1 cubic feet per second, so we make the threshold narrower, it's only happening now since 2000. So really low flows, or since 1999, about somewhere in there. The really low flows are only common then. And if you go one more step to less than 0.01 cubic feet per second, which is essentially zero, that's only happening in 2 years, 2016 and 2022. So this is my evidence that drought is becoming more common, that the river is experiencing more drought stress. Notice, I didn't point this out, but notice these numbers are different here on this axis. So the most common here is something like 140, but this axis up here only goes to 75, and that axis up there only goes to 20, which is what you expect because those data are included in here. I didn't ban them. They're all inclusive there. Does that make sense? We okay? All right. So I tried to look what particular years. So I picked the years that were the worst, and I calculated the minimum flow for every year. So this is the lowest flow you can get. And when you see that color change, it means there's another year interacting with it. So when these two colors blend together, like here, those two colors come together, and it changes the color. So this is my evidence that these years are really driving these very low flows. it's a little hard to see there because it's over the whole year. But if we go here, just look at that and blow it up, you can see a little bit more. But still, it's a little hard to see. I'm not very happy with this. But you can start to see that more and more that it's these 2 years that are driving things. But even here and here, this is 2002 to 1999. You know, they're there. They were low too. Any questions about that? Yeah.
Rob, I would guess that, you know, as devastating as it is in an individual year to have 3 or 4 months in a row, or a low flow period be at 1 or 0.1 or 0.01.
Yeah.
It's very significant, but really environmental damage probably will occur when you have multiple years in a row, and maybe it's like 5 or 4 or 3 CFS instead of the really low stuff. If you do it 2, 3, 4, 5 years in a row, did you get a chance to look at that at all?
Not at all. I think that's a very fundamental point that I can't address with these data at all, because I have no measure of the health of the river compared to at the moment. But I'm sure that what you're saying is true. And I'll just say this to people. As a biologist, what I believe is that biological systems are incredibly resilient. They're really good at recovery. But at the same time, they're incredibly fragile. So it's that unique combination that we face. And as Peter has pointed out, there's some threshold, and you go over that threshold and it's gone. All of a sudden, some part of the system, some piece of it is gone. And it's very hard to know. It seems to be different for different pieces. What I think is happening right now is that the fish are really suffering in the Parker. They've gone back to a few holes, so these bullfrogs especially are all in a few holes. And that the hooded McGinders will not be able to use these resources for a couple of years until these fish populations come back. I think they're there. I think they can reproduce. I think they come back. The water was really low in the marsh next to my house for months. This morning there were 50 mallards, 12 canaries, and a wood duck there. They were back feeding. They, you know, looks like nothing happened. But I don't think I'm going to see the hooded McGinders staying there come spring. I just don't think there's. But I may be wrong. You know, I don't know enough about the biology of the hooded McGinders. I'm afraid I'm going over time. How am I doing? I don't want to run over time. I'm not paying enough close enough attention. Am I over time?
A little bit.
Okay, I should stop because we want everybody to have time to speak about their important messages. I'll tell you one more thing, though. I'll just show you this one thing. 1 cubic foot per second is about 7.5 gallons per second. And we always measuring withdrawal in gallons, not in cubic feet per second. If a person uses 50 gallons in a day, that's standard what we use. That means this flow rate could provide one person's water needs in 6.7 seconds. So 1 flow per second is a lot for a person. That's pretty good. A cubic foot per second could provide 10 people water in 1 minute and 7 seconds. Okay, so that's pretty cool. That river really has a lot of water. You can't consume that water, right? But that's 12,000 or 13,000 people per day at 1 cubic foot per second. So what I'm saying is that the water we need in Georgetown for a day is about 1 cubic foot per second. So when the river gets down to that low level, we're pumping as much as the river has, taking all of it. Okay? And you can look at that from a slightly different point of view. Here I just did the calculations this way. Roughly speaking, the town pumps 500,000 gallons per day in the cooler months with a population of 8,400 people. That's 5.8 gallons per second or 0.77 cubic feet per second. So that's what's interesting. It's about the flow of the river. In the winter, it doesn't matter. At 10 gallons per second, who cares? Cubic feet per second. That's a fraction of the river. But in the summer, it could be as much as 150% of what the river has. So I'll just stop. There's lots more I can talk about, and we'll have a chance to do that. I'll just zoom through this. Is the next set of slides up? Okay. There's all kinds of data there about rain flow and evapotranspiration and, oh, sorry. There you go. Sorry, I apologize for going home.